mechanism that consists of this piston, or whatever that might be, that when you push this, and in this case you're exerting a force of 100 Newton, this is connected to a linkage that is pinned to this block, and it moves this other block that slides on this bar, okay? Let's call this A and B. So what we want to do, we want to keep this system in equilibrium by applying a force P downward on this piece. And there is a friction between this and, of course, the rod. Coefficient of friction is given as 0.2. So we want to know, and no friction here on these two surfaces. So we want to know how much that force, applied force P, should be to keep this system in equilibrium. In other words, no motion takes place anywhere. So remember again, in friction, we have two types of problems. One, that the problem statement explicitly states if the system is in equilibrium, no motion, no slippage, whatever ways it is stated. And the second case, that you need to verify if the equilibrium exists. So we have these two cases. And since the problem statement here says, find P that keeps the system in equilibrium, we would immediately recognize this is part one type of problem. In fact, the problem statement is find the minimum P. Okay. So what is the procedure? Draw a free-body diagram of all pieces. You have this block here subjected to this lateral force of 100 Newton. It is a sliding, so there's a reaction force N, and then due to this bar, which is a two-force member, there will be a force of FAV resisting that motion. So this is the free body diagram of this box, or this piece, right? Obviously, this AV is a two-force member, so we do have forces like this. And then we have this piece subjected to the force P that you want to find. And then obviously there is a normal load and V, and this, of course, force FAB. Now, what is would be the direction of the friction force that will be generated there? Up or down? It depends. We don't know. It may be up, it may be down, depending on whether this force is enough to push this up, so the friction force would be down. If it is not enough, it would be coming down. So you should consider both cases, and then find which one of those would be the minimum force, right? So I'm going to consider both cases. So if this is going to potentially go up, the friction force at B would be down, right? So this is the case if this goes up. If the force of P is large enough, okay, that may actually create a motion this way, so the friction force would be like this. If it goes, I'm sorry, if it goes down. Okay? So I call this, okay, Freebody diagram 2, this is 2 prime. Any questions? Yes.
So if we're trying to find the smallest value of p, couldn't we say that it would probably be going down because
You can.
it's going to be close to?
That is correct. You can, absolutely. In fact, that is the case. But if you do not detect that or visualize that, you cannot figure that out, that's the way to do it.
Okay.
Yes. If you do it that way, definitely, and you argue, make that kind of an argument, you're right. And you're not gonna spend more time than needed. Let's put it this way. So let's look at these two free body diagrams then. And again, I emphasize the difference between friction and frame problems is in the frame problems, you need to find all the unknowns from these free body diagrams. In friction, you only find those unknowns that you only need to find the unknown that the problem is asking you. What it is here, for instance, you want to find P. So you can see that in this free body diagram, the only unknown that you need from this free body diagram is this. So if I write equations of equilibrium then, in this free body diagram, I would just suffice that to write summation of forces along x equal to 0. I don't need an A. I'm not going to use it. And that free body diagram is not going to help me with finding P. So I just find FAB only. Oh, by the way, this is 60 degrees. So you have 100 minus FAB cosine 60, which is 1/2, is equal to 0. So FAB is 200 Newton. Okay. So I can now go here. Let's consider this one. I will just write summation of forces along x is equal to 0. So I have FAB, which is 200, right? And this is 60 degrees. So 200 cosine 60 minus n b equal to 0. So this is 1/2, and b is 100 Newton. Okay? And this, the problem states that this is not moving. So f of b would be 0.2 times nb, or would be 20 Newton, right? So now I write summation of forces along y is equal to 0 then. I have FAB cosine of 30, which f of AB is 200, cosine 30, which is square root 3 over 2, minus P minus FB, which is 20, is equal to 0. This is 174 divided by, 174 times 100, so it's 174 minus 20, almost would be 154 Newton. Okay. If you use this one, you can see that you would need to deduct this force, right? I'm sorry, add that force. Let's write it down anyway. So if you consider the other one, the only, this part doesn't change, it's only this one. So in that case, for the case of 2 prime, your summation of forces along y equals 0 would be negative p plus 20, right, plus 200 square root 3 over 2 is equal to 0. So P comes out to be, right, 194, right? Newton. So obviously, this is the case. Any questions? Yes?
Could we have used the, whole thing, Freebody Diagram in this too?
You mean as far to find this?
Yeah, I'd like to find
But
and B.
you need this force though.
Okay,
You need that force.
but couldn't we have just like summed the forces in X to find NB?
Well, if you sum the forces along X, right, you can find this NB, right? Then how about sum of the forces about Y? Then you have this force, which is unknown. No shortcuts. Do you have to draw all the free body diagrams? Any other questions? Yes?
Did you just not include the hole because you know it's not necessary?
Right, exactly, right. We just know that this is a sliding on these bolts, so the only force between them is a force of friction.
The normal and reaction.
Right, the normal and the, right, and I'm talking about as this is going up or down.
Okay.
Any other questions? So let's do another good problem. And the problem that I'm going to do a couple of years ago was a final exam problem, so it gives you a taste of at least what. In fact, most of these friction problems that I've done so far have been final exam problems, but this one was a good final exam problem. So, not that the other ones were bad, but this one was better. I like it because it gives you a good sort of a picture of all these concepts that I've been emphasizing in. For instance, how to detect whether you have equilibrium or not equilibrium, and so on. So this is the problem. You have a rod, okay, is laying against this wall, and on this end is residing or resting on a box on this floor. Let me call this surface A and this top part B, and this point of connection C. Okay? So we have this is of course, this rod has a weight. What we want to do, we want to apply a torque or a moment M and find out what is the value or what is the magnitude of the moment that can be applied in such a way that this rod doesn't move along this wall or stays stationary at that point, okay? So if this rod stays stationary at this point, due to the application of this moment, how much is that moment? But if this rod stays stationary there, that doesn't necessarily guarantee that the whole system is going to stay in equilibrium. So the question is, if we do that, if we apply a moment that can guarantee this is going to stay in equilibrium, would the whole system be in equilibrium? Meaning that if the friction force is here and here, now we have two surfaces, that we need to verify if the equilibrium can be satisfied at both surfaces. Okay? Let me give you all the information, of course, that you need. This height is 0.8 meters. This distance between the wall and the center of this box where the tip of this bar is touching, or point B is 0.6. The box has a dimension of 0.2 meters, height of 0.3 meters. Both rod and the box have weights, they're not weightless. So this one, I call that weight 2. This one has weight 1. This one has a mass of 3 kilogram. Consider G as 10 meters per second squared. So that would give me the weight of 30 Newton. Oh, yeah, that's right. This one has a mass of 6 kilogram. That will give me a weight of 60 Newton. Okay. What else you need? I think you have all the information that you need. Oh no, the coefficient of friction along these two surfaces, I call that mu sub A, is 0.4, and along these two surfaces, coefficient of friction is 0.6, and here is 0.2, or 0.3. So find M that keeps the rod at equilibrium against wall C. In other words, does not let the bar slip along that wall. So this is case 2, because there are some questions here as far as the validity or the assurance of equilibrium. So no magic, we start again with the free body diagram, right? So first, I would draw the free body diagram of this bar. If this bar moves due to the action of this rotational action, obviously it's going to go down. So the force of friction at C would be this way, and that would be mu at C times N C, because that we are told is we want that to stay in equilibrium. This is NC. We have the weight of 60 Newton here, and the applied moment M. If this bar moves this way due to that rotation, this tip will have the tendency of moving in this direction. So if it's going to move in this direction, what is the potential direction of the force of friction? That way, right? And there's a force at B here, right? So that's the free body diagram of the ball. Now, how about the box? Obviously, this box has a weight of 30 Newton. We also have this force NB that comes due to the contact with that, right? And we have also a vertical force and A. But here, if this is the force of friction acting on this bar, on top of this box, we will have the force of friction acting this way, right? So that is the only force acting on this box that will have the tendency of moving the box that way, right? So the friction force then on the floor or along the floor then should be in the opposite direction. So as you can see in this problem, in order to draw the free body diagram of the second piece or part of the problem, you really need to think very carefully how the motion may occur. And that's really the key. In contrast to frame problems, you could make any assumption as far as those forces of contact or connection, and then your solution leads to a negative number, so you change the sign. In friction problems, you have to establish the correct direction. Yes?
Is there no x component of NB even though the member is at an angle?
You mean here?
Yeah, so the member's at an angle, it's gonna be exerting a force at an angle, like if there's no
Yeah,
member.
it's almost like a roller here, right? A roller that has friction. So the only force would be the normal reaction, right? The X component is that friction force, right? Which we have if there was no friction force, right? You had only this here, you just had the vertical force, right?
So we're not trying to see if the box slides,
We are trying to see if the box slides.
but if there's no x component of, like if the member is not exerting any x component force.
This is the X component.
Oh.
The friction force
Okay.
that would be the friction force, right? Any other question? Yes?
Sorry.
Oh, no problem.
Doesn't friction come from, isn't it kind of like a reaction of, like, there's no friction in like resisting movement this direction
Right.
until I move my phone, right?
Right, that's right.
But
And
there's-
that's what is happening here. Because when you apply this, right, it is trying to move this ball, right, with respect to the box. So since this is gonna move with respect to the box, and it's gonna move this way, that means along the surface of contact, since the bar is moving in this direction, the friction force that is resisting its motion would be opposite to the direction of motion, right? So now using law of action and reaction, then correspondingly, the force acting on the box would be, that same force, FB, would be in this direction. And this is, given that this is the force that is going to cause sliding or motion of this box, what is resisting that motion along this surface is a friction force that would be the opposite potential direction of motion that this is causing, because the potential motion this is going to cause would be this direction. So the friction force is in the opposite. Right? Any questions? Okay. So let's just start with this guy. So I will start with, yeah, Freebody Diagram. One, two, then 3 questions of equilibrium. So I will write summation of forces along x is equal to 0. That will give me negative nc, right, plus fb is equal to 0. So I have fb is equal to nc. That is one equation. Okay. We write summation of forces along y is equal to 0. So I have nb, okay, minus 60 Newton plus fc, or plus 0.3 times nc is equal to 0, right? So nb plus 0.3 nc is equal to 60. That is the second equation. It's the equation of equilibrium. Then I can take summation of moments about point B is equal to 0. Point B. So these two, of course, cancel out. They don't generate any. This is going to generate a positive moment. We have this distance 0.6. So I have FC, which is again 0.3, and C times that distance, which is 0.6. Then NC, this distance is 0.8, positive again. NC times 0.8. I have that M, which is negative, clockwise, and then 64 Newton force generates a moment of negative 60 times 0.3 is equal to 0. So we can simplify this a little bit. This is 0.18, 0.8, 0.98, and C minus M is equal to 18. So this is another equation. So we exhausted all the equations that we have for that free body diagram. So we go to the next one, which is this one, free body diagram 2. Let me label this corner as point O, okay? So again, write summation of forces along X is equal to 0. That will give me FA minus FB, that's it, equal to 0, or FA is equal to FB. These are the two friction forces, right? Summation of forces along Y is equal to 0 will give me NA minus NB minus 30 is equal to 0, or NA minus NB is equal to 30, okay? And I will write summation of moments about point O. If I write summation of moments about point O is equal to 0, I will have FB times this distance is 0.3. So I have FB times 0.3 plus NA times 0.1. Then I have those vertical forces both generate a negative moment. So I have negative NB times 0.1, negative 30 times 0.1 is equal to 0. So this can be also simplified. That would give me, okay, 3FB plus NA minus NB is equal to, okay, 30. Okay, so we just need to find all the unknowns by solving these equations. So I'm going to give you all the answers that you need. You solve for all of those, you'll get M, that resolves to be about 8.6 Newton meter. NB will be 51 Newton, and A comes out at 80 Newton. FA and FB will be the same, in fact equal to F and C, and that would be 27 Newton. Okay. But wait, we haven't finished yet, right? Because we don't know if the box is moving or not. All we know is these are the friction forces that would be generated here. If they're less than the maximum friction force that can develop there, obviously there is no motion. But if they're bigger, obviously motion takes place at those points of contact. So we need to find the maximum friction forces at both points. Let's first find at A. At A, the maximum force of friction would be coefficient of friction given as 0.4, what it was, right? Wasn't it? Yes, 0.4 times NA, which is this. So it would be 32 Newton, right? So F of A, force that develops there, is less than 32, is 27. So no motion takes place there. At B, the maximum force of friction that would develop would be 0.6 coefficient of friction times MB, so it would be 0.6 times this, so about 31.6, okay? Again, f of B is less than 31.6, because this is 27, and this was also 27. So no motion takes place there either, because those forces are less than the maximum friction force that is developed there. So for this value of M, then we are confident that the system is not going to move at any potential location that motion may take place. So it's completely in equilibrium. Any questions? So problems of friction can be a little bit sometimes not tricky, but thinking requires some thinking. Remember the concepts though. Identify which case you have, draw the free body diagram, find the unknowns. In the second case, the big difference is that do not assume that these forces are the maximum force of friction. Just find the actual friction force develops and compare that against the maximum force of friction. If it is less than that, equilibrium exists. If it's more than that, you're violating it. Okay? No questions? I think I did another problem here in the other section. So why don't I do that? I think we can finish it in 4 minutes. It's not bad. That's not bad. At least we can set it up. Okay. So here's another interesting problem. You have a guy who's trying to pull this crate along this rough surface. The crate weighs 100, I would actually give it as 1,500 Newton is the weight, okay? So it's connected to a cable or a rope, and this guy is trying to pull it, okay? This guy weighs 800 Newton, about 80 kilograms. Okay. Coefficient of friction here, coefficient of friction at C is given as 0.3. Coefficient of friction between this guy's shoes and the ground, so I call it M, is 0.4. So we want to determine if this weighs 1,500 Newton, what are the, I mean, basically, is this guy going to slip, given that he's wearing this kind of shoes, or he needs to go and find better shoes? That's basically the question. Is this guy going to slip or not? Or can basically, with confidence, pull that crane? So what's going to happen? If this guy is going to pull that crane, that means maximum force of friction develops here that he has to overcome, right? So let's draw both free body diagrams again. You have this force, MC, weight of this box, 1,500 Newton, and then this guy, oh, by the way, this angle is given as 30 degrees. So this guy is pulling this, 30 degrees. So if this is going to move, it's going to move in that direction, so the friction force would be this, and obviously, we're talking about the impending motion, the maximum friction force, so that'll be 0.3 mc. That's the free body diagram of this box. But when it comes to this young man here, right, we do not know if this is the maximum friction force or not. But we know that if potentially this guy slips, would slip this way, so the force of friction would be this way, and we have a vertical force here, and this guy's weight, which is 800 Newton. So that's the free body diagram of the guy. So if you want, I can quickly do this, solve the problem. From the first free body diagram, again, do not find more, more than the unknown that you need. So that's what I would do here, right? So you write summation of forces along x is equal to 0. So you have P cosine 30 minus f of c, which is 0.3 nc is equal to 0. Summation of forces along y is equal to 0. You have negative 1500 plus P cosine of 60, right? Plus nc is equal to 0. So you can find P and nc. I only find P because that's all I need. P comes out to be 434.5 Newton, right? Which is all I need for this diagram to find the unknown that I'm looking for. So you go to free body diagram 2. So in free body diagram 2, you write summation of forces along x is equal to 0. So you have P cosine of 30 degrees, negative obviously, plus f of m is equal to 0. Substitute for P, you will get f of m, which comes out as 376.3 Newton. Then the second equation of equilibrium, it gives you what? You have Nm minus 800 Newton minus P cosine of 60 is equal to 0. So that will give you the vertical force that comes out to be 1002.
Isn't it
Sine 60?
sine 30, thank you.
Right.
Gotcha.
So that's correct?
Yeah.
Okay. So now the question is, we found the friction force between this guy's shoes and the ground. So is this guy going to slip or is not going to slip? The answer is clear, right? If you need to find the maximum friction force that generates between the guy's shoes and the floor. That maximum force would be 0.4 times Nm, or 0.4 times this, which is what, 400.8, right? So the friction force is 408, right? But what is F of M? The friction force that is generated as a result of this guy pulling this. Only 376, so 376 is less than 400, so the guy is not going to slip or slide or whatever, because his shoes are not going to generate that much force to overcome the maximum force of friction. Okay, great, thank you very much. See you on Wednesday.